Hello everyone. Today we are going to talk about the radiation intensity of an antenna array. Remember what we have done in the last lectures. We have illustrated the structure of an antenna array. Suppose we have an antenna array pointing to uh, Z directions. The total electric field that can be received in the far destination is given by E naught, which is the individual antenna radiations, and then times a factor. This factor is so-called array factor. Now sine and then n phi divided by 2, and then sine phi. And what is phi? Phi here is the phase difference between two labeling elements. It is given by kd cos theta. And alpha here is the progressive phasor. It is an artificially added phasor. And theta here is the direction, the angle, the polar angle indicating the direction of the destination. And K here is the wave number. So pi divided by lambda. And D is the spacing between two labeling elements. So this is the spacing D. And finally, we have another term. We have the last term in the electric field. And this term will determine the direction of the electric field. And this term also depends on phi. It is a complex term. It doesn't have any information about the magnitude. And today we are trying to make use of all this information to work out the intensity. And now we know that the electric field is given by this amount. And we know that the maximum value of this array factor is given by n. This is the amount when phi is 0. So I better write down everything. So we have no compare. It is sine and when when phi is equal to 0. So if you work out carefully, this one will eventually end up with 1. Yes. This should be n. I'm sorry about that. Yes. Now, the next thing that we are now looking at is the normalized array vector. The normalized array vector is so-called AF, and then with a subscript N is equals to the array factor AF divided by AF maximum. And do not forget that you have to take the absolute value. And if this is the case, then we are going to get an N. And if the distance here is substantially small, what we are going to get here is another expression. Is approximately equals to the normalized intensity is rho n. When is un is given by uh, the electric field I mean this variable time and if we substitute the value of phi according to this equation here, we will get n and then k d cosine theta divided by 2. And the bottom expression will correspondingly k d cosine theta divided by 2. And don't forget that the whole expression has to be squared. And now what we need to do for the next step is to work out the average intensity. This average intensity is also normalized. I mean, by normalized, it means it has been divided by the maximum. So the average and normalized intensity is equal to U O N. is total power radiation, but it is normalized, divided by 4 pi, and it is equal to 4 pi and then AF. And this expression is difficult to evaluate, but we need to use some trick. So yeah, we are going to free up this space. So UN, UON, the average and normalized intensity is going to be 1/4 pi 2 pi, and then the AF square, the normalized intensity, sine n k d cos theta divided by 2. And you have to do this sine theta, d cos theta, and then d phi. And let's assume this value as z. So let z be this value. And according to here, d z is equals to minus n divided by 2 kd sine theta d theta. And based on this information, we know that theta is going to be 2, and then d z divided by n k d. And how about the limit? When the beta is 0, and what is this value? When beta is 0, uh, z is going to be nkd divided by 2. So when beta is equal to pi, then this one is going to be cosine pi is minus with this in mind, we can simplify this expression. Yeah, U average and n is equal to 4 pi, and then we have 2 pi here. I'm going to move this to the first integral, and then we are going to do this minus nkd divided by 2, nkd divided by 2. and then sine z divided by z, dz. And suppose the antenna array is very large. Suppose the antenna array is large. The array is the large one. Then k and d divided by 2 is trending to infinity. Trending to infinity. And uh, the other one is minus kd over 2 is trending to minus infinity. So the whole integral become u times the um, so let's say this is equation 4. 4 becomes u no n, and I'm going to simplify this on the fly, and this one will become infinitive sine dv, and this value is approximately given as pi. So with this in mind, we basically resolve everything. Uh, let's see. We missed something, right? We missed something. So we need to multiply this with this one. And this one multiplied by 2. So the final value, if you do it carefully, this one will end up with a value pi divided by n kd. And based on this value, we can even work out the directivity. And but this directivity is going to be resolved next time. And if you have any question, um, please leave your question to the comments box. Otherwise, you just close this episode. Thank you.